In this video, we're going to look at a problem concerning different maxima and minima. In this case, what we're going to look at is finding the absolute max and min values of a given function on the closed interval -4 to 5. Now, the reason why the absolute max min values is important and the reason we have a closed interval is kind of important is something I want to touch on a little bit later. But first, what I want to kind of talk about is we're always told to kind of look at these problems and say, find these values, find these things. But how do we know that they exist? A large part of the time we know that they exist because we can find them through operations and everything, and we know how to find them. But we want to kind of ask ourselves why they exist, or do they even exist? And in this case, when we talk about absolute max and mins, we know that for our function here, or for any function in that case rather, and a given interval, the extreme value theorem is going to guarantee that they exist in our interval. So without a whole lot of proof into that matter of the extreme value theorem and getting too far into the details of that, just know that when we're faced with a problem of absolute max and mins, absolute max and min values, and a closed interval, we can always find them because the extreme value theorem and what it says. It says that an absolute max or min will occur inside, not necessarily inside of an interval, but on a closed interval. Now, the reason why I say on a closed interval is because the absolute max and min values of our function could occur at the endpoints. But what we've been concerned with so far has been local max and mins. And we know that local max and mins, local extrema, can only occur at critical points. And critical points are only allowed to occur inside of our interval, on the interior of our interval. So instead of having a closed interval, -4 to 5, we'd have an open interval, say, that looks like this. Everything between -4 and 5, but does not include -4 and 5. And we'd evaluate any and all critical points that we could find inside of that open interval. In this case, we're going to evaluate not only the endpoints to find our absolute max and min values, but we also have to include those critical points inside of our potential candidates for being the absolute max and mins of our functions on this interval, -4 to 5. So in order to do that, let's go ahead and evaluate our endpoints first, so we have those values at the ready after we get done evaluating how to find the other critical points for our function, and then we can compare those different values to see which one's the highest, which one's the lowest, because whatever value returns the highest value will be our absolute max, whatever value returns our lowest value will be our absolute min value. And now the preface of this values after absolute max and mins is not telling us to find the x coordinate on our interval that gives us the max or min. We actually want to know what the value of that absolute max or min is. So whatever output we get from plugging in the number in question that we're evaluating in our interval. Okay? So when we plug in -4 into our f of x, and we do this in the calculator, because I don't know what e to the 4 is and how to multiply that with -4 to the 4th, so it gets pretty big numbers, so I have the calculator do it for me, and it works out to be approximately, those are horrible approximately's, those look like birds. Let me put the values thing back. Those look like birds. Let me just erase this thing. So f of -4 evaluates to be approximately, that looks better, 13,977, and then we'll go to 3 decimal places, and that gives us 0.126. Okay? And similarly, we're going to evaluate f of 5, because that's our other endpoint, and f of 5 works out to be approximately, that looks a little bit better, 4.211. Okay? So we have something as large as 13,977 and something as small as 4 that we're dealing with right now. So we've evaluated the different values that our endpoints will give us if we plug them into the function, but now we need to go through and find the critical points of this function and evaluate those by plugging those x values back into our function to get a different value. And how do we find critical points? But taking the derivative and finding what x values make that derivative either equal to 0 or undefined. So without further ado, let's go ahead and take the derivative of this thing right here. And what we see is we have x to the 4th times e to the -x. So we have a function times another function inside of here. So we're going to need to use the product rule. Okay? So if we call this g and we call this h, what we're going to get is g equals x to the 4th, g prime equals e to the -x, g prime, actually this is going to be h, I'm sorry, I got ahead of myself. And then h over here is going to be e to the negative x. G prime is going to be the derivative of g, so that's 4x cubed. And then h prime is the derivative of e to the negative x. And so in this case, we know that normally e to the x's derivative is e to the x. So what that means is this is going to be the same thing up here, but what we do when we have something that's other than just plain old x in our power, we have to take the derivative of that power and then multiply this by that thing. So then what's the derivative of negative x, right? And the derivative of negative x is just negative 1. So then we multiply e to the negative x times negative 1, and we get negative e to the negative x, okay? And then following the product rule notation, what we're going to get is we're going to multiply g times h prime, and then add that to h times g prime. So what we get is we get negative x to the fourth e to the negative x plus 4x cubed e to the negative x. And this is our derivative right here that we're dealing with. Okay, so we've derived it. Now we need to look at the cases where the derivative could be equal to 0 and the derivative could be undefined. And all we're going to really look at in this case is just the values of x that make this derivative function rather 0. Because this derivative function is really defined for all x, especially all the x's on our interval. There's no dividing by zeros that we can see, no natural logs, no instances where we could take the square root of a negative number. So what we're going to end up doing is only finding the values that make this equal to 0 because there's no points where this derivative could be undefined. Okay, so what we're going to do is we're going to set this equal to 0 and solve this as best we can. So we're going to rewrite everything that we have here. So we got this going on. Okay, so now looking at this and this big old mess, it's kind of hard to see what could possibly make this equal to 0. So what I'm going to do to make this easier on myself is I see that because of this plus, we can look at this and this individually in terms of factors that this term and this term have in common, because this is all multiplication of terms, and this is all, again, a product of different terms. So what happens is when we add these two together, we can look at these piece by piece and factor out things to make it a little bit easier on ourselves to know what we're looking for. And what I see right off the bat is that they both have factors of e to the negative x involved in them. So we can factor them out, but then what about these x terms here? Well, I see that we have negative x to the fourth and 4x cubed. So I can factor out x to the third out of both of these terms, and here I'd be left with negative x to the 1, and here I'd be left with 4. So what I'm gonna factor out, just kind of making a little note to myself, is e to the negative x times x cubed. And what that's going to give us for this equation now that we have down here is going to be e to the negative x cubed, times, and we take x cubed out of this, we're left with just negative x. E to the negative x, we factored that out, so we're just left with the 1 there. Then we get plus, we factored out all of these x cubes, right? So we're left with this 4 times 1, and then we get e to the negative x. Since we factored that out, we're left with just a times 1 again. So now taking care of all these times 1s using the multiplicative identity property, what we're going to have inside of our parentheses is negative x plus 4. Okay, so we've simplified this a little bit and helped ourselves in that regard, but now you're probably wondering, well, how did this really help us? You guys remember something from pre-calc called the zero product property that I'm going to abbreviate as ZPP? What we use that notion for is that if A times B equals 0, we had the case either A was 0, B was 0, or a special case where both of them could be 0. Or not A, B, A, or both 0. Sorry about that. Both equal 0. We use this to find zeros of polynomials after we got them into factored form, because once we factored a polynomial and set it equal to 0, we could set each individual factor that we found equal to 0 to solve for the x value that made that binomial, in that case, after we factored, say, a quadratic. We would be able to find the x value that made that binomial equal to 0. We're going to use that same kind of thinking here, because what do we have inside of this equation right here but e to the negative x times x cubed times negative x plus 4. So all three of these things being multiplied together give us 0. that means that we can set each of these individually equal to 0 and solve for the values of x that make each individual thing 0 in their own right, and those will give us our critical points for our derivative. Okay, so let's go ahead and do that. We have e to the negative x equals 0, x cubed equals 0, and negative x plus 4 equals 0. Okay, since I have a negative x here, what I'm going to do is I'm going to add it to the other side and take care of that negative sign real quick. So I'm going to see that 4 equals x. So in this case, an x value of 4 would make this equation true. It would give us a 0 equals 0 type of statement here. But what that means for us is that 4 is a critical point, and so long as it is inside of our interval, which it is, it qualifies as a critical point. So x equals 4 is a critical point. Now let's solve for another one. If we take the cubed root of x cubed here, that was a horrible looking radical, but if we take the cubed root of both sides of this to cancel away the cube power, we're going to get x equals the cubed root of 0, or 0. And we know that 0 is inside of our interval, so that's another critical point we need to analyze. But now, what about e to the negative x equals 0? I ask you guys a question. Is this ever true? Is there ever a x value that we can plug into e to the negative x to get a return value of 0? And the answer is no. Because if you look back at the parent function of e to the x, it's a special type of exponential that looks something like this, right? It kind of skirts along the x-axis and just shoots up, e to the x, right? So what that means is there's always a horizontal asymptote at 0 in this case. And what that means is we can always approach 0 in this case, kind of coming at all these different values as we grow larger and larger in the negative direction. But we are never going to get a x value that returns this. We're never going to get an x value that we can plug in to give us e to that negative x value is going to give us 0. And actually, if we're looking at the graph for this situation, e to the negative x would be graphed more like this. It's a reflection across the y-axis. This was just e to the x, and this is going to be e to the negative x. I should have specified that earlier. So we're not worried about critical points that could make this statement true. But we did find 2 other critical points here. So now, let's go back to our original spot where we were evaluating these values to find our absolute max and mins and see what we get here. So if we do f of 0 and f of 4 and evaluate those, let's see what happens and whether or not one of them could be our absolute max or min. Well, when we plug in 0 to our original function, we get 0 to the 4th times e to the 0, which is 0 times 1, or 0, right? Because 0 raised to any power is 0. When you put e raised to 0, anything raised to 0 gives you 1. 0 times 1 is 0, okay? What about f of 4? Well, here again, I plugged this into my calculator, and I got 4.689, okay? So what I'm seeing here is that I have the lowest value occurs at x equals 0, and it gives us a absolute min value of 0. This is our absolute min because it's the lowest value out of the critical points and the endpoints that we evaluated. And then if I look at f of negative 4, I see that in this list it is by far the largest value. So then this will give us our absolute maximum. Or this is our absolute maximum value, rather. Our absolute max occurs at x equals negative 4. So the key difference in absolute max and min versus relative max and min, when you're looking at absolute max and mins, you need to incorporate the endpoints of your interval. But you also need to still keep in mind that you're also looking for critical points on the interior of your interval. So relative max and mins can only occur inside of your interval, but absolute max and mins occur on your interval. And so how that translates is that they can occur inside of your interval, like we saw with the absolute min in this case, or they could occur on your interval on one of the endpoints of your interval.